Hello, hello, Mohammed. Hello.
Yes.
Yeah. Please start. I have already started the recording,
Okay.
so please
Okay.
you can start the class.
So is my screen visible?
Yes, sir, visible, sir.
Okay, that's good. So let me give you a brief introduction about me, and then I will start discussing about the quantum Fourier transform. So I'm a PhD student at the University of Michigan, Ann Arbor. I'm a third year PhD student, and I'm currently working in quantum information theory. My background is from electrical engineering, and I completed my bachelor's from IIT Hyderabad, and then I started my PhD here in the University of Michigan. So today, as we all know, like I will be discussing about this quantum Fourier transform. So I don't know much about the background we have, like all of you guys have. So I thought maybe we should start with some of the motivation that from where this quantum Fourier transform came, and it will be very brief, maybe like 10 minutes, and then we will jump into the quantum Fourier transform, the actual quantum Fourier transform. So I will start with the classical Fourier transform. So from where it originates from the maths perspective. So the Fourier transform. So the Fourier comes from the mathematician whose name was, I think, Joseph Fourier, and he kind of bring the Fourier series thing into picture. And then so the Fourier series is basically that you are able to write any function is as a sum of cosines, so as a function of some sinusoidals. So maybe I will share what I mean. Yeah, so this is what I was talking about, that we can write any function as a sum of some sinusoidals. So let's say we have this square function, and we want to write it as a sum of the sinusoidal waves. So let's say I want to see this function f1 of x. So this one is a sinusoidal whose frequency is some 2 pi, and with some amplitude 4 by pi, and with some shift pi by 2. And we have another function here, which is this f of 2. This one is like high frequency as compared to the above, and also the low amplitude. So what we will get if we sum up this f1 and f2, so we will get this green one. So this one has like a more amplitude, which is coming from the f1, and the more frequency, which is coming from the f2. So this is what, so I want to approximate the square wave function using the sum of sinusoidals. And this is what I will do. So I will here, so I wrote a function that does the sum of the sinusoidals, and this is what it shows. So this is just for one single sinusoidals, but let's say I increase the sum. So as we will increase, we can see that we are getting the square wave function. And as we increase more number of sinusoidals, then it will approximate to the square wave function. So there are some ripples at the top, which can be filtered using some kind of filtering and other things. So this is what I mean, that any function can be written as a sum of the sinusoidals, which is basically the result of this Fourier series. So now we'll go to the Fourier transform. So let's say we have the time domain signal x of t. For example, here I have just drawn this ECG signal. So this is the ECG signal in the time domain. So we have the x-axis as a time and the y-axis as the amplitude, and this is what the ECG signals look like. But we can't infer much from this time domain signal. So there is no any kind of inference that we can get from this time domain signal. So what we can do is we can change the basis. So instead of time, we can uh, do some change of basis, and we can analyze the same signal, same ECG signal in some other domain. So what we will do is we will transform this time domain signal into a frequency domain signal, which is written as or denoted as S of f. And from S of f, from this frequency domain signal, we can go back to the time domain signal by doing this inverse Fourier transform. So how this transformation looks like? So the transformation looks like this. We have what we have here in the red box. So this one is the frequency domain signal, and this one is the time domain signal. We do some kind of integration here over the time t, and it can be from any range from minus infinity to infinity, and then we get this frequency domain signal. And similarly, for the inverse Fourier transform is the same as the previous one, but here instead of -1 we have +1. So that's the only difference between these two, and the functions get reversed. So here we have the frequency domain signal, and here we can get the time domain signal. So this is all about continuous. So when we have this continuous signal, then this Fourier transform and all these integrations works well. But in general, in the practical sense, we don't have that kind of memory that we can store the infinite number of the values, because the real numbers can't be represented using the finite number of bits, so with high precision. So that's why what we do is we generally take the samples. So we do the sampling of this time domain signal, and we try to get the Fourier transform uh, of that sampled signals. So what we will do is we will do the sampling here. So sampling will be like at t naught you will take, and let's say t naught plus some alpha, and then this will be some, so this will be some t naught plus 2 alpha, and then we will take t naught plus 3 alpha. So alpha is defined by some other theory, that how much alpha you can take and what you can do, so that you have some good amount of samples. So from this, we will now go to the discrete Fourier transform. So we'll have like this. So we have the samples now. So instead of x of t, we did the sampling. And when we did the sampling, we have now x of, let's say, 1, x of 2, or maybe simply I will denote as x1, x2, just for the sake of good looking, that maybe it is now only x1, x2 till xn. So we have taken n samples. Let's say the time is from some t naught t naught to let's say some tn. We have taken some time within some time period, within some time limit. We have taken n samples. So now the discrete Fourier transform, it looks like you have x of f, or maybe we can denote as xk. So k here represents again the indices of the sampled version in the frequency domain. So this x, this one is kind of x of f and sampled at some k. So this will be summation over n equals to 1 to, or let's say I started here with n x0. So n equals to 0 to n minus 1, and this one is n minus 1. So this will be xi, and then e raised to minus 2 pi I k n by n. So this is what the discrete Fourier transform looks like. So we have just we have did nothing. We have just sampled the original signal x of t, and we have taken n samples here, and then from their n samples we have created the samples of the frequency domain signal x of f. So we have this x of f, and from here we have created the sampled version of xk. So all these things we just do for the sake of the space. We don't have the infinite space to store all the signal, the time domain signal here. So this is what it looks like if you see. So let's say we have the original signal, which is a kind of like high amplitude and high frequency signals. So if we do the discrete Fourier transform of this, so we can see these three spikes. So these three spikes says that you have a frequency of 495 hertz, you have a frequency of 500 hertz, and you have a frequency of 505 hertz in the signal, in this time domain signal. So this is what we have seen also in the previous Fourier series example, that if we do the summation of three sinusoidals, so here like sine, some function of sine, let's say 2 pi 495 hertz t with some phase, and if we do again sine with some amplitude a1 with some amplitude a2 sine 2 pi 500 t plus phi plus a3 sine 2 pi and 505 t plus phi, we will get this signal back. So this is what that's the benefit of working in the Fourier basis, or the Fourier domain instead of just time domain, because we get a lot of other inference also. So that will be clear here in this example, the corrupted signal. So we have this original signal, but let's say we have transmitted this signal through some environment, or through some, we did some kind of processing or computation, we applied some algorithms, some filtering, some analog circuits, anything we applied, and we get this kind of signals. So this one is like very noisy. We can see here in the middle part here, it's very noisy. So noisy means you have a very high frequency signal that is more or less you can't distinguish. It's very noisy. That's what we see. Let's say during, I think when we have this CRT monitor, so we have all this black dots. So those are kind of like high noisy things. And this is actually clear. So this is actually clear from this frequency domain transform. So when we transform the time domain signal into the frequency domain signal, so this spectrum is what from coming from the original signal. This is our original signal, and this one is the noise. So we can see here it's very high in amplitude also, and it's very let's say far away from the original signal, the frequency of the original signal. So we know that, okay, so we got some other signal also got added up in my signal, and we have to kind of do some processing to remove it. And that's the main benefit of working in the Fourier transform, that we can simply apply a filter that it's called low pass filter. So what it means is we can just take this part and we will pass it to so we will pass the whole signal, but the filter will do it, it will only take care of this low frequency signals, and it will just delete this high frequency signal. So that's the main benefit of working in the frequency domain. So with this, I just kind of gave some introduction to from where this quantum Fourier transform and what's the main motivation of doing all these things comes. And now I'll start with the quantum Fourier transform. So I had other examples also for this Fourier series here, but yeah. So we have here, we can see this one is the original signal. We want to approximate using some sinusoidals. So here, this one is just a straight line. You can say zero frequency kind of sinusoidals, and this one is some low frequency. This one is medium. This one is high, and we add up all these things. We can get a similar, like almost similar, not exactly, but similar kind of curve which we have here, the original function. But if we do the sum after like for 49 sinusoidals, then we can approximate our function very well.
Sir,
So
can we say that this Fourier transform is used to convert digital to analog?
no, so digital to analog is different.
Like sir,
So
in earlier diagram you showed, no, it was a like straight line graph and you converted into a continuous curved graph like this one here.
This one, the so we said this one.
No, this original function, you converted it into a continuous wave like thing. No, this some sinusoidal below.
Yeah, so this one is also continuous. So I just tried to approximate this continuous function, some random continuous function as a sum of sinusoidals. So this one is not digital. And this one is also continuous.
Yeah, I mean, this is not digital. Digital is like square wave, but I meant to say that the sharp edges become like curved. You can say it becomes a,
Yes,
wave like graph.
that's correct. Yeah. So yeah, but I understood. I think you mean digital like this, a square wave.
Yeah, yeah, yeah. So
So
this might become like a sine wave kind of thing.
yeah, we can approximate using the sine wave. That's what this Fourier thing means, that you can approximate. So it doesn't mean that you have the square. It is, so this one is called as a square wave. So
Yeah, this is the digital signal.
yeah, this one is not actually digital signal. This is also analog in some sense because you have one here, you have zero here, and it is like a continuous. So analog is continuous, and digital is discrete when we say. But it actually most of the people they use these terms interchangeably with this square wave function. So that's a completely different thing. But yeah, so these here, the wave here, these waves are actually undesired thing. This is not what we desired, but this is a good approximation what we can say just for the analysis purpose. So do we have any other questions before we start with the quantum Fourier transform?
No, sir.
Okay, I think okay, so we are good to go with yeah. So this was the motivation for using this Fourier transform. uh, and now now we had to see how this quantum Fourier transforms are used in this quantum computing. So there are many algorithms that I think we will cover in the later part of this course as we go on. So the first one is Shor's algorithm, world famous Shor's algorithm. It uses quantum Fourier transform. The second one is quantum phase estimation. Quantum phase estimation and many others algorithms also that uses the quantum phase estimation. So indirectly, it also uses the quantum Fourier transform. So that's Grover's algorithm. So all these things I think we will cover next in few weeks. So Grover's algorithm and then quantum counting and other things. So the quantum Fourier transform has many important. It's an important building block of all these algorithms. So yeah, just to recall that we have this discrete Fourier transform. Discrete Fourier transform, so that transforms a vector. Let's say I denote it as x, which is x naught, x1 up to xn minus 1. So we have n samples here, and it's a vector of n size, n length, and it maps it to some vector. So this one is discrete Fourier transform. So this maps to some other vector that is also in n length. So y1 till yn minus 1, and each of this y are denoted can be written as so 1 by root n summation g equals to 0 to n minus 1. So this one is kind of interesting thing. So this one actually adds a phase in each of the signal, And the main thing about the phase comes from the sinusoids, because in the sinusoids we have the phase. So for each of the samples we'll add some phase, and then we get some other vector, and this vector is what the, you can say, the Fourier basis or Fourier vectors kind of, or you can say Fourier basis. So this is what and this e raised to 2 pi I j k, this is just the Euler notation. We have this uh, cos theta plus I sine theta. So now this one is from the classical. So we have this DFT, we have the vector, and we got the another vector which is known as the Fourier vector or the Fourier basis. And now we will do the same on the quantum. We will now transform it to the quantum. So the quantum Fourier transform. So we have the basis state in the quantum Fourier transform. So let's say the basis state is some let's say it's j. I just denoted as j. And what it will do is the quantum Fourier transform. It will transform it to 1 by root n. So I denote this one as omega jk and subscript n. So subscript n, just to emphasize that it's n length. And so we are working with the n length vector, and jk is the kind of like indices. So here this j coming from the x and k is coming from the y. So that I will write it here, omega jk and subscript n, and this one is k. So basically we have this basis. So for example, let's say computational basis. We have a computational basis that is 0 1, and we transform it to the superposition of other bases. So superpositions of, so we get some other superposition. So for each basis, for example here computational basis, we get a superposition. So this is what the quantum Fourier transform is doing. So if we try to write the unitary for this quantum Fourier transform, because in quantum every operations has to be implemented uh, through a unitary matrix. So we have the unitary matrix also for this Fourier transform, so which we write as q uqft. So before writing this, let me also explain. So this one is just for a single basis. So this one is just for a single basis, but we write generally a general state, let's say psi of a quantum state, as some superposition of the basis states. So let's say like this, j is equals to something over j. If we have the computational basis, then we generally write for this case we write psi as alpha 0 plus beta 1. We only know about for single basis how the single basis transforms into QFT to some other superpositions. So let's say some 0 tilde, how it get transformed. So but now we have to write for this complete state. So what will be the QFT for this complete state? So that we'll write it here. So let's say we have a state x, which is summation over j equals to 0 to n minus 1 xj j. So this is some general quantum state, and these j's are the basis. So these are orthonormal basis. So these are orthogonal, and also they are normalized. So that's why they are orthonormal basis. And we will do the Fourier transform here. So after doing the Fourier transform, we will get the state y, which is a quantum state, and it's written as summation over k equals to 0 to n minus 1 yk and k. So here the yk is actually this value. So yk is this one. So this one is what yk. So so in some sense, what we are trying to do here is we are trying to use our discrete Fourier transform, which is this one, and we try to do the discrete Fourier transform on the amplitude of the state. So we have the amplitude vector here. We take this xj. So we take the xj, which is the amplitude of all the basis vector here for this quantum state x, and we try to apply the discrete Fourier transform on the amplitude. And so when we try to do the discrete Fourier transform and on the amplitude, so we will get the amplitude of the new vector in the Fourier domain. So this is what we are trying to do. So we have this quantum state, and the amplitude with respect to each of the orthonormal bases, we have this xj, and we are trying to do the discrete Fourier transform on this xj, and whatever this value will get for each of k equals to 1 to sorry k equals to 0 to n minus 1, we'll put this here in the state of this y. So this is what the discrete Fourier transform is. This is what the quantum Fourier transform is. So we have all these quantum states here. So now we have to write the unitary matrix for this quantum Fourier transform. So we can apply this unitary matrix on any state, and we will get the quantum Fourier transform of that state. So the unitary matrix for this QFT is written as, so we have 1 by, so let me write like this. You have j equals to 0 to n minus 1. So this can be understood from here, this part. So for each of the j, so for each of the j, what we are trying to do is, sorry, this one is the opposite. J, yeah. So for each of the j, what we are trying to do is we are transforming each of the j into this vector. So, and this one is what is here. So for each of the j, we are transforming into this part. So if we just simply try to get the other vector y, so let's say we have using this unitary, let's say we have this x, which is equals to summation j equals to 0 to n minus 1 xj j. Let's use a different index here, j I, and now we will apply the unitary operator on this state qft. So this will be, so qft on the x, so this will be summation over j equals to 0 to n minus 1 summation k 0 to, and then we have j here, and then we apply the x here, summation over I equals to 0 to n minus 1 xi I. So what we will have here in this part, so in this part we will have summation over xi, sorry, summation over I 0 to n minus 1 xi, and then this j inner product with I, and this is equals to 1 if I equals to j, and this is equals to 0 if I not equals to j. So basically we get I equals to j. So the final thing will write as j equals to 0 to n minus 1. The same thing here. The same this one. And then we'll have here xi. So xi will become xj because here it is 1 only for I equals to j. And this j inner product with I will become 1 here. So we'll have only xj. So this xj will go inside. So this will become xj. And then we have k here. And if we try to simplify this further, so we'll have 1 over root n summation over k equals to z, summation over j equals to 0 to n minus 1, summation k equals to 0 to n minus 1, omega n j k xj, and then k. So we can do some change of order. So we will change the order here and maybe write like this: summation k equals to 0 to n minus 1, 1 over root n. And this is what we have yk. So this will get summation k equals to 0 to n minus 1, yk, k, and this one is y. So that's how we wrote this part, the y. So we started, so let me summarize. So we started with this QFT transformation just for the single basis. So for single basis, we will write as the summation with some normalization here. So this is just for the normalization that our state is normalized in the quantum case. Otherwise, we can put or we can't put. It's doesn't matter in the actual DFT. But for the quantum, it is very important because we have to normalize the state also. So that's why we put 1 by root n. And we have this kind of transformation here, which is 1 by root n summation over k n samples. And this omega, which is defined here, e raised to 2 pi I j k by n. And we'll write the basis transformation in the QFT for the QFT as this. So then we showed that, okay, so for the for every quantum evolution or every quantum operation, we have to write the unitary to perform that. So we wrote the unitary here. So for each of the basis vector j, so this is orthonormal basis again. And for each of this orthonormal basis, we get the another vector, which is which comes from here, this part, this green box. And then we claimed kind of thing that we have a vector x, a general state, because here we only discussed for the basis. But for a general quantum state, that is the superposition of the orthonormal basis, what will be the Fourier transform? So we claimed that, yeah, it looks something like this. It looks something like this. So, and the coefficients here is the DFT of the xi, the coefficients of the quantum state x. So we claimed that. And here, using the unitary operator for this quantum Fourier transform, we showed that indeed it is the case. So this is what the Fourier transform, you can say the Fourier transform formula is. So the mathematical form of the quantum Fourier transform is what we have just discussed. So now let's do a quick example for this one qubit case. So we'll do the example for this 1-qubit case.
So
So
like in Grover search, sir, these are the rotations that are discrete. Like you move some angle theta, and finally you reach the result. So sir,
yes,
what is the use of applying Fourier transform in this?
in the Grovers,
Yes, sir.
so in the Grovers, if you see, you don't actually apply the quantum Fourier transform explicitly there. You apply what is called quantum phase estimation. So in the quantum phase estimations, it comes the quantum Fourier transform inverse. And maybe I think in the next part we will see that why we actually have a quantum Fourier transform in the quantum phase estimation or in the Grover's algorithm at the surface. So maybe when I will try to show the QFT for a bit kind of thing, like when you represent a vector in a bit form, so then I think it will be more clear. But I think, yeah, it's a good question. So I will definitely try to touch also on that maybe in few minutes. So let
Okay.
me just quickly go through the qubit example here, one qubit example. So, so we have this one qubit. So we have the basis 0 and 1 for this one. So this one is the computational basis, and we start from this basis. So this is what we start. And so we can write a general state psi for this part as alpha 0 plus beta 1. And here this will be our x naught. This will be our x1. And we have n, that the number of samples. Generally what I see is n equals to 2. So for this one qubit case, so now we will write the amplitude of the other transformed version. So we have this psi and we apply the QFT, and let's say we get some y, and this y, as we have seen, that this can be written as some yk. Sorry, this one is y0, 0 plus y1, 1. So we have to now derive, find what is y0. So y0 is we have to write, we have to use this formula here. So this one yk is 1 by root n. So yk is 1 over root n summation j equals to 0 to n minus 1 omega jkn. And if we try to expand this, it will be 2 raised to 2 pi. I is this imaginary number, 2 pi I jk by n. And then here we will have this xj. So similarly, we can do the same thing here. So it will be 1 by root 2 because n is 2. And then we have x0. So x0 is alpha. And then we will write e raised to, so I'll write exponential here. And that will be 2 pi I. And our j is also 0. K is also 0. And n is 2. Then we will write x1, that is beta, exponential 2 pi I, and our j here is 1, k is yeah, so our j is 1 here and k is 0 because k here is 0, that's why we are finding y0. So we will have 1 0 by 2. So this is what we have, and we get alpha plus beta by root 2. So similarly for k equals to 1, that is y1, we will do again the same thing. So I write the same thing, but here these things will change. So j will be 0, but k will be 1, and here it will be, both will be 1. So we'll get alpha minus beta by root 2. So our new vector, so let's say we represent it as y, this will be 1 by root 2 alpha plus beta 0 plus 1 by root 2 alpha minus beta 1. So this is what we get. So what this means is that if you apply the QFT for this 2 qubit psi, so we will get this 1 by root 2. So psi is any general quantum state in this two-dimensional for the 1 qubit. So we will get this 1 by beta 0 plus 1 by root 2 alpha minus beta 1. So with some simple observations, actually we can also see the explicit uh, the matrix or the operation or the operator which is basically doing this unitary of the quantum Fourier transform, and this is, so we claim that this one is Hadamard operator. And why we are saying this UQFT is a Hadamard operator? Because of this kind of like a special structure here in the state, the output state of this unitary Fourier, the Fourier transform operation. So if let's we know that this quantum Hadamard operator looks like this. So we have 1 1 1 and minus 1 here. Okay, so 1 1 1 minus 1 here. And if we just apply to h psi, we will get the same thing here, alpha plus beta by root 2 0 plus alpha minus beta by root 2 1. So comparing these and comparing these equations, we can clearly see that okay, our unitary for this quantum Fourier transform is nothing but the Hadamard. So for n equals to 2, so Hadamard operator, the h does quantum Fourier transform on psi. So this is the example for n equals to 2. Similarly, we can do for any number of qubits. But for doing any number of qubits, because when we, let's say when we write for 2 qubit, so we have here the representation as this 0 0 0 1 1 0 and then 1 1. So here in all the Fourier transform, we have done all these Fourier things here using some number, right? So we have this k equals to 0 to n minus 1. We doesn't give it a binary representation, but mostly we write all these qubits in the form of binary. We don't write as 0 or 1 2 and 3. So we don't write like this. We generally prefer to write in the binary form of that. So now we will try to derive a formula, we can say that, and that will be actually helpful to answer your question also for the Grover's algorithm. And that will be also helpful to understand how to find the circuit for this quantum Fourier transform. So we don't write like this one here, a 0. So what we will try to do now is try to find the quantum Fourier transform for larger n, not for just this one qubit, for larger n, and for this larger number of qubits that we represent generally in the computational that we generally represent using some binary notation. So how does the quantum Fourier transform will look like in that case? So let's say our n is now 2 raised to n, and then we have the state here. So we have the state x, let's say, which is denoted which can be written as x1 up to xn, and these xi's are actually binary. This belongs to 0 1. So similarly here, like for example, this one is x, x1 x2, so x1 equals to 0 and x2 equals to 0. So we have this representation now, and now we will apply this quantum Fourier transform on this x. So we'll do the same thing here as we did previously, 1 by root n summation y equals to 0 to n minus 1 omega n xy, we'll write y. So yeah, this is the what we have. So we know that this x, or earlier we have this j, and it goes through some quantum Fourier transform. It goes to 1 by root n summation over k equals to 0 to n minus 1 omega j k n k. So here we are just using the same thing, but we are kind of now using in the form of x and y just to make it more readable. So we have again the unity for this quantum Fourier transform. It takes the basis. So this one is some orthonormal basis, and it takes, so generally it's like a computational basis, what we say in the quantum computing literature. So we have this unity, it works, it applies on, it acts on this computational basis, and we'll get this state. And this is same as this, except the index is different now. So now we will expand this one. So 1 by 1 over root n, then summation over y equals to 0 to n minus 1, and then this one is exponential 2 pi I, and then xy. So by n, so n we will write as 2 raised to n, because here we have said we are doing this analysis for n equals to 2 raised to n. So 2 raised to n, and then we have this y. And now we will try to write this y. So generally in these definitions, when we write here, so we don't say that k is written in the form of computer, in a binary form. We say k is some number which is from 0 to n minus 1. Similarly here also, that y is some number from 0 to n minus 1, but now we'll write y as a binary, in the binary form. So recall that we can write actually a binary form like this. So let's say if we have decimal to binary conversion basically. So we have decimal to binary. So we write something like this. You have 4, let's say 3. So we have this 1 into 2 raised to 1 plus 1 into 2 raised to 0. So this is what we try to write. But so here generally, so we have to divide this by 2 raised to 1 and then add 2 raised to 1 and then take the binary form of this and then do. So what I'm trying to say here is, so we write this y, which is like a decimal number, as some I k. Let's use a different here. So k equals to 0 to k equals to 1 to n. Yeah, k equals to 1 to n. And this one is yk by 2 raised to k. So this n is the number of bits we are choosing. So this represent number of bits. So for 3 we are using only 2 bits. So that's why we have this. So this is what we are trying to write here in the fractional binary notation. So in some, so representing y as fractional binary notation, which is y equals to some y1, y2, yn. So that will now become 1 over root n summation y equals to 0 to n minus 1 exponential 2 pi I. Then x will come here, and then we have this yk by root 2k, k 0 to n. And then we have this y1. So this one is actually by y by n. Yeah, because we are using this fractional binary notation. So that's why this y by n will be like this, not y. So y1, y2 up to yn. So this is what we have now. So here we have the summation inside the exponential that we can take out, and we can write as so we can write as a product here. So with same index y1 to n e raised to 2 pi I x yk by 2 raised to k y1, y2, yn. So now we have to make some observations here, how this looks like and what is happening here. So now what I will try to do here is, so we'll try to write this as a tensor product of the summations of like this. So let me write and then we can go through it. 1 over root n, then tensored over k equals to 1 to n. This one is 0 plus e raised to 2 pi I x over 2 raised to k, and then we have this 1. So if we try to expand this here, it looks something like this. So we have 0 plus e raised to 2 pi I. So let me write like this: 2 pi I x by 2, 1, then tensored with 0 plus e raised to 2 pi 2 square, 1, and similarly we have to do tensor product over till n times. So we'll have here,
Hello,
yes,
hello, Mohammed.
yeah, yeah,
Yeah, great teaching. So I was just curious to know, like, the class timings are over. So, would you like to continue tomorrow? Because tomorrow we have 2 2 hour
yeah, sure,
uh,
sure, sure,
class timings.
sure, sure. Okay,
So yeah, it's not necessary that you have to take the full 2 hour. You can take like how much as you want. Maybe you
okay,
can
okay.
distribute it like, like according to Indian time, it's like morning and then evening.
Yes.
So I mean, you can distribute your content accordingly.
So maybe I will only take the the evening session, because morning will be uh it will be a
Oh
midnight.
yeah, because you're in the US, right?
Yeah,
So
so morning
according to
will be
time
very
zone, it might
difficult.
not be suitable for you.
That's correct. Yeah. So
No
yeah,
issues.
maybe I can stop here, and then tomorrow again we will meet and we'll go through this analysis, and then we'll go to the circuit part, how to derive the circuit,
Yeah,
and just to end. So just to end this class with a question that someone asked during the lecture, that how this quantum Fourier transform comes into the picture of this Grover's algorithm. So the answer basically lies in this last equation, last form, so last line, and here it is mainly because of this structure that we get from the quantum phase estimation. So after phase estimation we get a similar kind of a structure, so this structure. So then we apply inverse of the quantum Fourier transform, and we try to get only a number here. So instead of all these summations, we just try to do some inverse Fourier transform and we try to get this part only. So that's where the quantum Fourier transform actually comes into picture, because of this expression. So yeah, I think now we can end the
sure. Thank
part,
you. Thank
and
you
then
so much.
tomorrow we'll again continue.
Yeah, sure, sure. So
Okay.
I will stop recording.
Okay, sure. Thank you.
Yeah, thank you. Thank you so much.
Yeah, thank you all.
Thank you, everyone.